Hi everyone, I hope this video finds you well. Today we are going to talk about rational functions. So my hope is that at this stage in the game, you have already looked at those functions that I had for you on your document. And today we're going to look at those characteristics and talk about why they are appearing the way that they're appearing. So let me share my screen with you. I have all the graphs pulled up already. Okay, so this is what the functions look like when they're all graphed on the same screen. Very overwhelming when you look at them all at once. In fact, I always like to joke that these graphs, when you put them all together, make me think of like a subway system. Have you ever been to New York or like Washington, D.C. or Chicago or something? This is what it looks like when you try to read those train maps or whatever. You take the red line, which connects with the green line, and then you're going to hop on the blue line from there. Yeah, anyways, so for your main observations at this point, my hope is that your main takeaway is, these graphs are kind of weird because, for instance, they almost all are disjointed in some way. Like this first one, f of x, has two very distinct portions to it. There's this upper right-hand region and then this lower left-hand region. And then the next one, g of x, also has two regions, upper left, lower right. Now h of x, he looks like a little blip on the map, kind of strange, but nonetheless, he does not appear to be separated into regions, so that's interesting. And then my personal favorite, j of x, seems to have three distinct regions. You've got the lower left region, the upper right region, and then this cubic looking third degree wannabe function in the middle. So very interesting on that one. And then the last graph, k of x, also has two very distinct regions. Okay, so the first thing I want us to talk about is, why are these graphs separated into regions? And the reason for that, ladies and gents, is because rational functions, as you see by their definition, are fraction functions. A rational function, think ratio, fraction. So rational, ratio with an N, rational functions are fractions. And since they are fractions, you are running into an algebraic snafu of sorts. Do you like my word choice there? So this graph definitely breaks apart. I'm on f of x right now. This graph definitely breaks apart. And if you were to estimate with your eyeballs as to where that breaking point is, it appears to be somewhere between -5 and -10. Like this graph over here definitely goes beyond the -5. So it's definitely, you know, it makes its way to the left of -5. And on this side of the world, it definitely makes its way to the right of -10. But somewhere in between the -5 and the -10, they seem to break apart. Well, let's look back at the function. Somewhere between -5 and -10. Well, I'm just going to have to give it away because we're not in person to explore this together. Hey guys, they break apart at -8. That's where the breaking point is for those two graphs. Now, why is it -8? Well, I want you to think about what would happen if you plugged in -8. If you take 10 divided by -8 plus 8, it says undefined. So let's think about that. Why is it undefined? Well, what's -8 plus 8? -8 plus 8 is 0. And 10 divided by 0 is not possible. You can't take 10 and divide it into 0 groups or 0 partitions. What are we even doing? Are we even dividing at all? 10 divided by nothing. That doesn't even sound like division, if you ask me. So dividing by 0 is undefined in mathematics. It is not possible to divide by 0. Now, just really quick, going off on a quick tangent. 0 divided by 10, on the other hand, absolutely possible. 0 divided by 10 is 0. That is a computable, tangible answer. You have 0 and you divide it into 10 piles, 10 equal partitions. Well, I realize it still feels a little bit weird, but if I were to tell the whole room, hey guys, I have 0 cookies to share with you today, 0, and I'm now gonna share them with all of you. Well, how many cookies would each person get? Okay, none, because I had nothing to share. But at least you can imagine that there are 10, let's say, individuals sitting in front of me. And I'm now going to take nothing and divide it equally amongst them. Nothing for you, nothing for you, nothing for you. So 0 divided by 10 really is 0. But when you try to reverse that, 10 divided by 0, now is when it gets wacky. So I came to class with 10 cookies and I'm going to share it with nobody. How do I even start dividing out my 10 items if I have no groups or no piles or no partitions to divide up amongst? All of a sudden, it doesn't make any sense. And so dividing by 0 is a mathematical error. It's undefined. So since rational functions are fractions, we have to be ever cognizant of this error, because wherever that error is, you will see a break in the graph. So let's try to investigate this a little bit deeper now. So now that we've had the conversation that there is no such thing as dividing by 0, I'm going to switch to my little whiteboard here. So on the first one, like we said, it's -8, because if you have f of x equals 10 divided by x plus 8, well then the error, so to speak, of when the denominator would be 0 happens at -8. So the vertical break, so to speak, on that graph is at -8. So let's look at number 2, which is g of x. So g of x was 5x divided by 5x plus 4. So you'll notice on that graph that it absolutely does break apart. Let me go back to it really quick. There we go. So g of x absolutely breaks apart. It appears to be at negative something something. So I'm just kind of picturing it with my eyeballs and my mouse right here. It seems to be maybe around -1 that these graphs break apart. But guys, you're not going to eyeball it. This is not going to be an estimation technique. You need to figure out exactly where those graphs break apart. And the way that you do that is by trying to locate the error. So on that particular one, where is the error of that denominator? When will the denominator equal 0? Whenever that happens, you're going to have an error. It's impossible to divide by 0. So whenever this happens, you're going to have that breaking point. So just a little bit of algebra, and you will see that the breaking point for that graph is at -4/5, which is -0.8. Now remember when I eyeballed it, I was like, man, it's approximately -1. Okay, well, please don't say approximately -1. No, it's at -0.8. That's exactly where the graphs break apart. You can locate it exactly. Now, there's a couple in here, though, that are really interesting. One of which is this guy, h of x. So if you recall, h of x seemed to not break apart at all. It's just like a little blip on the graph, but nonetheless, it's a fluid blip. It doesn't separate into 2 parts. And so you're like, well, man, what's going on? How come this one doesn't have a break? Well, let's think about the algebra. So the denominator on that one was, let me clear this, The denominator on that one was 4x squared plus 16. So for h of x, numerator was negative 2x plus 5. Denominator was 4x squared plus 16. So remember, the errors come from the denominator. The only error we're speaking of right now is division by 0. No such thing as dividing by 0. So when does 4x squared plus 16 equal 0? Well, let's find out. So we could subtract 16. I'd have 4x squared equals negative 16. Divide by 4. So now x squared equals negative 4. Square root both sides. Hey y'all, what's the square root of negative 4? Is it 2? Is 2 squared negative 4? No. Oh, maybe it's negative 2. Is negative 2 times negative 2 negative 4? No. So what's the square root of negative 4? It's not possible. As far as the real number system goes, it's not possible. So in Math 121, you would have learned that this is actually, the answer to this is plus or minus 2i. It's imaginary. But nonetheless, in terms of the real number system, it's not possible. So as far as what number, real number, will cause the error, there are none. There is no real number that you could plug in here and actually have the answer come out as 0. So there is no real number that would actually cause this graph to break in half. Therefore, the graph does not break in half. There is no breaking point. There is no error point. So that's why this particular graph, it's the only one that did this, it did not break apart into two regions. It's fluid, it's smooth, it's continuous is what we call that. So the reason why though is because when you go hunting for your errors, again, it comes from the denominator. Well, this particular denominator, no real answer would produce an error. So it's simply not possible. And then of course, there's my favorite one, j of x. J of x seemed to break apart twice. It seemed to break apart somewhere around positive 4 or 5-ish. And it seems to break apart somewhere around negative 3-ish, okay? Please don't eyeball it. The errors that we're speaking of, what cause these graphs to break apart is if the denominator is equal to 0. So let's look at the j of x function and see if and when that happens. So for the j of x function, we had 3 times the quantity x minus 2 times the quantity x plus 4 all over quantity x minus 4 quantity x plus 3. Okay, so we're talking denominator. So when does the denominator equal 0? Well, guys, can you see why we had to finish polynomials before we could move on to this section? You've got yourself a little factored form right there, guys. Factored form, yep. What's the 0 of this factor? Positive 4. What's the 0 of that factor? Negative 3. You could, of course, do the algebra if you need to. X minus 4 equals 0. Simply add 4 to both sides. There you go. And x plus 3 equals 0. Simply subtract 3 from both sides. There you go. So this particular function, because it has that quadratic, that factored form quadratic on the bottom, yeah, there's 2 errors. There's 2 breaking points. So graphically speaking, you're going to see the graph split apart twice. That is why it breaks apart twice. It has 3 distinct regions. Okay, now everything we've just talked about with regards to errors, that is a vocab word. Those are called the vertical asymptote. And so you'll see definition-wise that a vertical asymptote is simply the value of the input variable that causes the error. And when we say error, once again, we mean division by 0. So as we move forward, we're going to talk horizontal asymptotes next. But as we move forward, please just know that, for instance, if I was graphing j of x, the expectation would be that you identify exactly where your vertical asymptotes are and that you graph them. They should be included in your graph, indicated by a dotted line. So as we move on and you start drawing more and more graphs for me in this section, the expectation will be that wherever your vertical or horizontal asymptotes are, you're going to indicate that with a dotted line. And not only does that communicate to me or any other reader of mathematics that you know exactly where the asymptotes are, but it also then helps guide your pencil, because when you're sketching these graphs, you have to stay within the boundaries of those asymptotes. Notice the actual function never, 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 never actually touches that number, because remember, that number is an error. So by drawing the dotted lines, it also helps guide your pencil to just know that as your pencil draws it, you're going to get really, really, really close to that barrier, but you're not going to touch the barrier because it simply approaches that number. So that's part of why we draw the dotted lines in there, okay? And then since those asymptotes are the errors of the function, it then also goes to conclude that your domain, remember that domain, all of the valid domain means valid values of the input, domain, valid values of the input. So if these numbers are your errors, aka your vertical asymptotes, well then the domain would be everything. You can plug in whatever you want, except those numbers. You can plug in everything except 4 and -3. So your vertical asymptote and your domain go hand in hand in the sense that as soon as you know where the errors are, the vertical asymptotes, well then your domain is simply everything but that, or everything but those, in this case, plural. And then if we were still talking about which one, the h of x, there's the little blip on the graph that had no errors at all, well then that domain is just all real numbers. No errors, so no qualms, it's just all real numbers. Okay, so hopefully that gives you a sense of why these graphs are breaking apart. We've got the vocab word vertical asymptote officially. The expectation, of course, is that you always identify them as x equals, or whatever the input variable is, but they have to be called by their input letter. And graphically speaking, they have to be indicated by a dotted line. All right, so that ends our vertical asymptote conversation. Stay tuned, we'll do horizontal asymptotes next.